Welcome to Intro to Material Sciences 101. Grab a seat, everyone. In today's explainer, we're embarking on a really fascinating journey to decode the physical universe right in front of us. Seriously, look around you right now. Your desk, your notebook, your pen, even the walls of the room you're sitting in. They're all made of something. But what exactly is that something? How do we understand it? How do we organize it? And how do we use it to actually build our world? Well, that is exactly what we're going to uncover today. So sharpen those pencils, open your minds, and let's get right into it.
You know, you might think material science is a purely modern discipline, something born in sterile, high-tech laboratories. But humans have literally been obsessing over materials since ancient times. Take this quote from the ancient Sanskrit text, the Rasaratna Samuchaya. It translates to, "The materials used to make the crucible are clay and iron." Even thousands of years ago, early scientists and artisans were carefully selecting very specific materials. They needed heat-resistant clay and durable iron to smelt and manipulate other substances. They understood that the world is built on a foundation of materials and that mastering them is the absolute key to progress.
All right, here is our roadmap for today's explainer. We'll be looking at the science of classification, observing material properties, water and solubility, measuring mass and volume, and finally, defining matter.
Let's start with Section 1, the science of classification. Before we can analyze the complexities of the physical world, we first have to learn how to bring some order to the chaos. So let's lay down our very first foundational rule. Classification is simply the method of arranging objects into groups based on a shared property. Think about your local grocery store. The grocer doesn't just toss everything into a giant mountain in the middle of the store, right? Spices are in one aisle, grains in another, fresh produce up front. They're classified by their shared properties so we can actually make sense of them. As scientists, we've got to apply this exact same logic to the materials that make up the universe.
Consider a totally random assortment of everyday objects: a lock, a key, a wooden block, maybe a pencil. Now compare those to abstract geometric shapes that are perfectly grouped by their form. How would you group the everyday items? Well, you could group them by what they are made of. You'd put all the metal objects, like the lock and key, in one pile, and the wooden objects, like the pencil and block, in another. Or, you could group them by their function or even their color. The property you choose completely dictates the classification. It's a deliberate analytical choice that we make.
Which brings us right into Section 2, observing material properties.
Once we know how to classify, we have to know exactly what properties we're looking for, because those properties determine an object's actual real-world utility. So let's think about this for a second. Why on earth is a tumbler or a cup made out of cloth a genuinely terrible idea for storing water? It sounds ridiculous, right? Because cloth is porous. It completely lacks the fundamental property required to hold a liquid. The big takeaway here is that we choose a material to make an object strictly depending on its properties and what we actually want that object to do. You wouldn't build a bridge out of paper, and you definitely wouldn't make a window out of concrete. Purpose dictates material.
So what are these properties we're observing? Let's start with appearance. We generally categorize materials into lustrous and non-lustrous. Lustrous materials naturally have a shiny surface. Think of freshly cut metals like iron, copper, or aluminium. Non-lustrous materials, on the other hand, are dull, things like paper, wood, or rubber. But here's a fun fact. Some metals can actually trick you. They might look super dull from long-term exposure to air and moisture, but if you take a piece of sandpaper to them or slice them right open, that brilliant metallic luster instantly reveals itself.
Next up is hardness. We contrast hard materials, which are super difficult to compress, against soft materials, which are easily compressed or scratched. But remember, scholars, hardness is incredibly relative. If you press on a kitchen sponge, it compresses easily. It's soft. A rubber tire is definitely harder than a sponge. But if you compare that rubber tire to a solid block of iron, suddenly the rubber seems pretty soft, doesn't it? We are always measuring these properties on a relative spectrum.
Now let's talk about light transmission. This is absolutely vital. We classify materials based on how well we can see through them. Transparent materials like clear glass, water, or even the air around us let light pass through completely. Opaque materials like a brick wall, solid wood, or thick cardboard block light entirely. And sitting right there in the middle are translucent materials, things like frosted glass or butter paper. They let a little bit of light through, but they scatter it so you only get this hazy, blurry view. Think about a game of hide and seek. If you hide behind a solid brick wall, you are perfectly concealed because the wall is opaque. If you hide behind a frosted glass door, you're somewhat visible as a fuzzy shape because the glass is translucent. But if you tried to hide behind a clear glass window, which is transparent, you'd be spotted instantly. See, these properties are constantly interacting with our everyday lives.
Okay, let's move into section 3, water and solubility.
It's time to put our lab coats on mentally. We're going to examine exactly how different materials interact with the universal solvent, water. Here are the rigorous steps we follow. First, we fill our glass tumblers about 2/3 with clean water. Second, we take a spoonful of our test material, let's use sugar for one glass and sand for another. Third, we stir vigorously and carefully observe what happens. Observation is the absolute bedrock of material science.
And here are the empirical results. In the first tumbler, the sugar has totally vanished into the water. We call this material soluble. It is completely dissolved. But in the second tumbler, no matter how long or how hard you stir, that sand remains stubbornly sitting right at the bottom. It just doesn't mix. We classify this material as insoluble. Water is uniquely powerful because it can dissolve such a massive variety of materials. That's precisely why it is so essential to the functioning of our own human bodies.
But hey, don't let your thinking get trapped strictly in solids. Solubility absolutely applies to liquids and gases too. Liquids like vinegar completely mix and dissolve in water. Even more incredibly, gases dissolve in water. The most critical example of this is oxygen. The oxygen gas dissolved in lakes, rivers, and oceans is the exact property that allows fish, aquatic plants, and entire marine ecosystems to literally breathe and survive. Without gas solubility, our oceans would be completely lifeless. Moving on to Section 4, measuring mass and volume. We've covered appearance, hardness, light transmission, and solubility. Now we've got to shift our focus to the concrete, measurable dimensions of materials. When we ask how heavy or light something is, we are fundamentally talking about its mass. Imagine putting 3 identical paper cups on a digital scale. If you fill one with water, one with sand, and leave one totally empty, the scale gives you entirely different readings. The cup with water is heavier than the empty cup. It has more mass. Mass is simply the property that quantifies the actual amount of matter present in an object.
Now, what about the physical space an object takes up? Well, that is what we call volume. If you pour a small amount of water into a glass, it only fills it halfway, right? It occupies a specific, limited amount of space. If you pour more water into an identical glass, it fills it right to the brim, occupying much more space. Even though those tumblers have the exact same capacity, the volume of water inside them is completely different. Volume is simply the measure of the space occupied.
Finally, we arrive at Section 5, defining matter. We have mass, we have volume. Let's synthesize all of these axioms to define matter itself. Please, write this down in capital letters in your notes. What is matter? Matter is absolutely anything that occupies space, meaning it has volume, and has mass. That's it. That is the golden rule. Water is matter. Sand is matter. The glass tumbler is matter. Your textbook is matter. If it takes up space and has mass, it belongs to the physical world of material science.
As scientists, we have to communicate our findings globally, which means we need a shared language of measurement. For this, we use the International System of Units, or the SI system. When we measure mass, we use kilograms, denoted by a lowercase kg, or grams for smaller items. When we measure volume, we use liters, denoted by a capital L, or milliliters, ml. You will see these units on every bottle of drinking water and every bag of rice you ever buy. They are the standard tools of our trade.
Before we wrap up, it's pretty awesome to connect our modern scientific definitions back to some profound ancient wisdom. Ayurveda, which is an ancient Indian medical system, actually classified physical matter using a highly sophisticated system of 20 opposite properties, or gunas. They contrasted guru, meaning heavy, with lagu, meaning light, ushna, or hot, with hima, or cold. It just goes to show you that the human drive to classify, measure, and truly understand the properties of matter is a deeply rooted ancient intellectual tradition.
And that brings today's explainer to a close, but I want to leave you all with a slightly provocative thought to chew on. Is air matter? Think about it. You can't see it, you can't easily hold it in your hands, but does it occupy space? Does it have mass? Ponder that tonight. Discuss it with your classmates, because finding the answer to that exact question is going to be the perfect starting point for our next class. Class dismissed, and thank you so much for joining me today.